Hi, welcome to Exponential Models Lesson 2. In order to run a model using an exponential function, we're going to want to be able to know how fast that model is changing or how fast the function is changing. So we're going to need to be able to work out the gradient of exponential functions, and that's what we're going to look at now. First of all, exponential growth looks something like this, okay, crossing through at y equals 1. And I'm going to call out the graph y equals e to the x. Okay, remembering that e is a very specific value, a little bit like pi. It's irrational. Its decimal equivalent is a long, never-ending number, but it's roughly 2.71828, etc., etc., etc. The reason we use it is it has some really interesting properties that we're going to look at in just a moment. So what is exponential growth? Exponential growth is essentially defined, or one way of defining it is it's growth where the rate of change, in this case growth or decay, is proportional to the current value of the function. There are lots of different examples of this in the real world. And one of them that you would have heard a lot about at the moment is the discussion about the spread of the coronavirus. When it initially came out, people were talking about exponential growth because the number of new infections, that is the growth, was proportional to the number of people currently infected. That is the value of the function at that moment in time. There are many other cases where this also is true. Radioactive decay is another example. So if you have a lump of uranium, the number of uranium atoms that are decaying and causing radiation is proportional to the number of uranium atoms that are actually in that block of uranium at the time. How can we write this down? So let's say we have here y equals a to the x. Then the rate of change is our gradient function, dy dx. And we're saying that that is proportional to a to the x. We could write, if we prefer, just y. It's proportional to y. So we can say, therefore, that dy dx equals some multiple, whatever, a number, of a to the x or y. And so this allows us to differentiate. We can go straight from there to there. But the problem is, what's this value k? This is where e comes in. Y equals e to the x has a very special property. Its gradient is equal, not proportional, but, well, it is proportional, but it is equal to e to the x, i.e. in this case, k equals 1. Okay, so if we come over to our graph on the left-hand side, and I take a point here and draw the tangent, okay, then the gradient of that graph is going to be equal to this x value here. In this case, let's say x is 1.5, so the gradient would be 1.5. Okay, and it has this very, very special property. And we're going to use this property here to help us when we are solving these problems. There is, however, one more property that is really, really important. That's going to help us generalize this a little bit further. Because we're not going to want to just deal with e to the x. What about y equals e? I'm going to end up using k again. Wind kx. This is a different k, okay, or it's similar actually. But anyway, and a rule that you will use later on in year 13. Something called the chain rule allows us to differentiate this. We will cover that and even prove it much later. And so here, for now, I'm just going to tell you the rule. And that is that the gradient of this function is affected by this k in such a way that it's just k times e to the kx. And so this gives us a second statement, a more general statement that we need to know. Okay, so this is the general statement that we're going to want to, for now, remember, and in the future we will prove much more. In fact, Khan Academy has some excellent videos about where E came from, who found it, and why it has those values. I've given you one very brief explanation that the gradient of y equals e to the x is e to the x itself. It is itself. But do watch the Khan Academy videos because they're very interesting. So let's see if we can use this property to help us. Oops, that was close. To help us solve a problem. So here we go. Okay. Using y equals e to the 2x, find the gradient when x is equal to 3. So if we've got y equals e to the 2x, then dy dx must be equal to k, where k in this case is 2, so 2e to the 2x. And at x equals 3, we can say that dy dx equals 2 times e to the power of 2 times x, which is just 3. So we've got 2e to the power 6. You could plug that into a calculator to get a decimal approximation, but there is our f to the power a. What about finding the value of x when the gradient is 10? Let's have a go at that one. So here we know that dy dx is equal to 10. So we can replace dy dx with the differential that we've already found. And this now allows us to solve this. So let's rearrange and solve. 2 to the x equals e to the 2x. Yeah, e to the 2x equals 5. Now we're going to need logarithms. I'm going to take ln of both sides, or you could use the definition of what a logarithm means. But I'm going to say, right, take ln of e to the 2x equals ln of 5. Ln of e, that inverse function, so I'm just going to be left with 2x equals ln of 5, so x equals ln 5 over 2. Again, you can find a decimal equivalent if you wanted to, but that is the exact answer. Finally, part C, find the gradient when y is equal to 2. So here we know y equals 2, but we also know that y is e to the 2x, so we can say e, oh no, sorry, forgive me, we want the gradient. We want the gradient. So we're going to go dy dx, we already know is equal to 2e to the 2x. But we already know that y is, as I said earlier, e to the 2x, that is the function. So here, we could rewrite that as dy dx equals 2 times y. we know that y is just 2, so we're going to get 2 times 2, so dy dx equals 4. I hope that's made sense. Please do watch that again. I've gone through that very, very quickly. Watch it again if you need to. We're going to move on. So what about y equals 2 to the x or y equals a to the x? We only know how to differentiate y equals e to the something x, kx. Well, what we need to do is rewrite 2 or a or whatever value it is as a power of e. If we can convert these things into this, then we can differentiate it. So let's have a go. Start with y equals 2 to the x. We're going to want to ask ourselves, what power e equals 2? i.e., e to the, let's pick a variable, let's say u, e to the power u equals 2. This is just an equation that we can solve using logarithms. You could take logs to both sides. This time I'm going to use the definition of what a logarithm is. So the definition of ln is the power that I need to raise e to get the number in the bracket. So we want a ln logarithm basically. What power do I have to raise e to get 2? Well, that must be the power that I need to raise e to get 2. So that must be equal to u. So e to the ln 2, e to the ln 2 equals 2. Okay. So that's all kind of an aside, really, because now what I can do is I can rewrite this equation. Y equals, instead of 2, I'm going to write e to the power of ln 2. So that's 2, and then 2 to the power of x. But our rules of indices allow us to rewrite that as y equals e to the power of ln 2 times x. Now we can differentiate. So to differentiate, so to differentiate, we can just write dy dx equals, we multiply by k, the number in front of the x, ln 2 e to the ln 2 of x. That part of the function doesn't change. The last thing to do is just tidy this up a little bit, so we can say dy dx is equal to ln 2, that doesn't really change, but e to the power of ln 2 is just 2, so we can multiply that by 2, and then it's all to the power of x, due to the x, and that is our simplified solution. Let's try more generally with y equals a to the power of x. So again, ask ourselves the question, what power of e equals a? And you don't have to write as much as I did there. We can just write e to u equals a. Okay, we could even now go, well, I know that's got to be ln a, because e ln a, the e and the ln are going to cancel, we're just going to be left with a, so that must be equal to a. There's our aside. That's the useful part of this that's going to allow us to convert this equation into this equation. Y equals e to the ln a times x. Now we can differentiate. So dy dx equals, multiplied by the constant in front of the x, ln a, times e to the power of ln a times x. So this part of the function hasn't changed, so the derivative is proportional to the function itself. Finally, tidy this up, e and ln, they're going to cancel. We're going to be left with dy dx equals ln of a multiplied by, this is going to leave us with a to the power of x. Again, you may need to watch that again. Take your time. Use the examples in the textbook. The textbook explains it very well indeed. You should now be able to answer all of exercise 8A. Have fun.